So let me just introduce the first speaker. Mike McCarthy, going to talk about exotic molecules in the laboratory and in space.
Well, thank you very much. It's certainly a great pleasure to be invited to this, this symposium, this workshop, and have the opportunity to tell you about some of the work that's going on at the Center for Astrophysics in Cambridge and with colleagues and collaborators, both here and abroad. So what I'd like to do in this talk is really focus on really the molecular astrophysics part of astrochemistry, specifically how we detect molecules in space and how we can be certain that they actually exist there. And that's what's going to be the focus of this presentation. I thought I would start by actually taking a couple steps backwards. And it's somewhat a cautionary note, but go back to before the advent of what we know to be molecular astrophysics and look at what the prevailing view of the time was about even the mere existence of molecules in space. And this is actually a portion of a famous talk by Eddington, who was a very accomplished astrophysicist. And he, in the Baking Lectures, he talks about molecules, or the possibility of existence of molecules. He said, quoting here, "It is difficult to admit the existence of molecules in interstellar space because once a molecule becomes disassociated, there seems no chance that the atoms will rejoin. Subsequently, they'll be ionized, and of course, they'll repel each other." So bottom line is, we know how molecules are destroyed. We don't know how they're formed. Therefore, there are none, right? So in fact, but he goes on to say, in fairness, this is if this seemingly fatal objection is overruled, the calculations are not unfavorable to molecular absorption as the cause of opacity in dark nebulae, which is precisely what we know to be the carriers, in fact. The reason I say this is because, again, as I'm a chemist by training, but it's almost overwhelming sometimes the ease with which we can destroy things, and nature is much more creative in making them than we are. So you've already seen with Eric and Paula a version of this slide. And this is just meant to illustrate that what we now know is that chemistry is truly universal and molecules are ubiquitous. We see molecules at every stage in the stellar evolution, and including, again, in regions and under situations which we think be completely inhospitable to the chemical bond in organic chemistry. We see complicated molecules, or in some cases quite simple molecules, at every stage, whether they're in supernova remnant, diffuse gas, this pre-stellar star formation region, all the way through planetary disks, and eventually, obviously, on Earth. And the point here is that molecules really are significant reservoirs for chemically active elements in nature. They're not just a fun game to play, so to speak. If we understand the molecules and their existence, we can therefore infer much about the chemistry and the physics, because things like H2 are very difficult to observe directly. So we use these as tracers to understand the chemistry and physics of these sources. All right, so this is a variation of what Paula showed. This is actually a plot showing you the rate of detections of molecules in space since the advent of molecular astrophysics in the early late 1930s. So following the work of Eddington, eventually astronomers found three simple molecules in space, CH, CH+, and CN, that did not fundamentally change their view of the harshness of the interstellar medium, and then it then consisted of, if you will, atoms, atomic ions, and really simple diatomic molecules. All right, that all changed in the late 1960s when OH was found, and then water and ammonia, and then the field has really taken off since then, and it shows no signs of flagging. The rate of detections is now, I had 220 on my list, and it's going at about 4 molecules per year. All right. Oh, okay. Oh, bend over. So, as already alluded to by Eric and Paula, most of the molecules we see in space are organic, and certainly that's true for polyatomic species. And the real drivers for understanding and detecting more molecules in space are two factors. Number one is better and more sensitive facilities. The real kingmaker here now is ALMA, which is an NSF facility. and really the importance of laboratory spectroscopy, because now we've gone really from a data poor field to a data rich field where we have very, very rich molecular spectra. And they don't come with labels on them. We have to figure out from the laboratory what we're observing. All right, so if we actually subdivide that, in fact, of the 220, about 10% are positively charged and about 5% are negatively charged. And I'll talk more about those in a moment. All right, so in fact, this area of molecular astrophysics is really a highly disciplinary subject. And the reason, in part, is a combination of factors. Number one, as already alluded to, the chemistry of space is not very often in thermodynamic equilibrium. So we get tremendous departures because we often have a kinetically controlled chemistry. So we see, as a result, high energy isomers. We see both positive and negatively charged molecules. I'll show you examples of metal-bearing molecules, these long carbon chains that Eric's alluded to, and even most recently, polar aromatic rings. And so in order to make progress in these areas, to detect and characterize these in the laboratory, we need contributions, obviously, from, in this case, radio astronomy, because that's the way in which we're observing these distant astronomical objects. So we need improved measurements, astronomical measurements. We need laboratory techniques that are sensitive, because these molecules, we can't buy many of these. We have to synthesize them. They're transient. Theoretical calculations play a very important role, because we need to predict the spectrum, at least approximately in advance, in often cases. We do need to do a lot of chemistry and chemical reactions to really understand the sequence of events that leads to these. I won't talk about it, but there are a big area of instrumentation and technology development. We need to adapt whenever possible to new approaches, new techniques, leverage things like high-speed digital communications and other things in our experiments. And again, I won't talk about it, but again, data management analysis tools are very important because, again, like biology, astrophysics has gone to high information content. Every radio telescope in the world has wide bandwidth, and we're getting thousands of gigabytes of data very quickly. So we need to really ultimately retool our techniques in the laboratory to address this data explosion, so to speak. So I thought I would start with a simple example illustrating, in fact, how we detect these molecules both in space and in the laboratory. And this is an example of this aforementioned dark molecular cloud in the Taurus constellation. So I'm not an astronomer by training. I really don't know where any stars are other than like the North Star. So this was actually taken by a colleague, Brett McGuire. He was in Green Bank, West Virginia. Took a picture of the northern sky with a camera. We correct for the rotation. It's about 2 hours of exposure. So to orient your eye, I will show you, in fact, parts of the constellation, which you can see here. So the Pleiades is the Seven Sisters. This is a very famous constellation, right? It's been known for hundreds and hundreds of years. And I apologize because now it's bright out. It's kind of hard, perhaps, to see part of the projector. But obviously, people have been fascinated with stars, and they're naturally gravitate towards starlight. But what I want to focus on instead, it's hard to see here, but there's a region in the sky which is dark. And this is what Paula mentioned as these dark molecular clouds, where because of higher density, gas and dust is absorbing and scattering radiation. So these are optically dark, right? And inside this one giant molecular cloud, where we know, again, there's tremendous amounts of molecular material, is a somewhat innocuous source called TMC1. All right, so if we look at that source, as already alluded to by Eric and Paula, this is optically dark, and we know that's because it's H2. So optically, there's nothing interesting to see here at all, right? But we know from a variety of observations, it's cold, it's probably 5 to 10 degrees, and it's very low density, 10 to the 4th. So by comparison, sea level is 10 to the 19th, right? So we are 14, 15 orders of magnitude less dense than we are at sea level. So that means a binary collision happens once every 2 weeks. But as alluded to, you have a lot of time in astronomy for these chemistry to ultimately evolve. All right, so obviously under those conditions, we have to have reactions that occur very quickly. There can't be any barriers. They have to go at the gas kinetic rate. And that's driven ultimately by cosmic rays. And we see these molecules primarily in radio emission, sometimes in infrared absorption. And of course, they're important because that's where we believe star formation occurs. So what I then will show you is if we point a radio telescope at this source TMC1, what do we see? So this in the far right is I think my laser pointer is not working anymore, but it's barely, okay, I guess if I punch really hard. So this is actually taken with the GBT telescope, which is in Green Bank, West Virginia. This is a fabulous facility. This is the largest steerable object on Earth. It's 100 meters in diameter. This picture does not show justice to it. So it's 100 meters from here to here. It's almost 500 feet tall. So it's an amazing facility. You should come visit if you can. They have public tours and things like that. And it's used, obviously, for radio astronomical observations. So if you point this telescope at this source at about, in this case, I'm showing you a very small part of the spectrum. This is a spectrum at 21 gigahertz. So by comparison, CO absorbs at 115. So this would be somewhat heavier molecules that we'd be looking at. And you see, after a few hours of irrigation, it's dominated by this one feature right here, this very strong feature. And if I blow that up for you, it's really razor sharp. It's 25 kilohertz at 21 gigahertz. So that's a part per million accuracy, right? So it's extremely quiescent in that sense, right? And we actually know the carrier of this line because, again, it's so sharp and it's an unusual molecule. And in fact, it's not even an unusual molecule. It's an isotopic species of an unusual molecule. And the carrier is CCS radical, which is an open shell radical. Of course, on Earth, sulfur-34 is roughly 1/20th the abundance of sulfur-32. And we know this because we have laboratory spectroscopy, and we can exactly compare the spectrum we measure in the laboratory to what is observed here. And we found other lines as well. So if I then put that aside, and I say, well, if that's a line, perhaps these other things here are lines as well. And this one I'll highlight for you. And we did this observation fairly recently. And this is actually now a doublet set of doublets. And we, too, know the carrier of this. And for the first time, this has been identified. And the carrier of this is, again, one of these carbon chains with one end is an oxygen, the other end is a hydrogen. And we know, again, because in red is the laboratory prediction. And it exactly overlaps. So we really have a spectral fingerprint in the laboratory which we can compare to what we observe in space. So there's no possibility we can be wrong. It's like the likelihood that I'll win or would have won Powerball, right? It didn't work out. Chances are like 1 in 300 million or something, right? So in fact, that's what we know, that we know that these identifications are extremely secure because we have very precise laboratory rest frequencies. All right, I will largely omit many of the details here, but other than to say we have in the laboratory quite sensitive instrumentation to measure these reactive molecules. Again, they're not things you can synthesize. We have to make them in things like an electrical discharge source or by laser ablation. They're formed for a short period of time. They expand. We can cool them down again to the temperature of TMC1 or colder, a few Kelvin, and we can monitor you can determine their rotational spectrum before they ultimately collide with the walls. All right, and we can do this for a variety of techniques. Ultimately, we can, for example, in the case of these electrical discharge, we make tens of different molecules simultaneously, right? So there's enough collisions that occur that reaction happens, chemistry, and then we freeze everything out. We measure things at very low temperature, and often that's the important component of theory. All right. So this is now just, let me show you a few examples of what we can do with laboratory astrophysics and how it's impactful and how we can then relate it to the astrophysics. So this is an example, again, kind of amplifying what Eric said. This tree from Oka and McCall, which is shown here, where we start with H2 plus, and by combinations of reactions with hydrogen and carbon, we can build up, in this case, of an I-molecule network to things as complicated as benzene. All right, so these are very important ions at low temperature and low density. They can be very powerful probes of things like fractional ionization that I'll show you in a moment, and we can infer things like the abundance of nonpolars. All right. So, and as we already alluded to, the beauty of the reason that we see many protonated molecules in space is because this H3 plus is actually only holding on to that proton quite weakly. So when it collides with almost any other molecule, it will exothermically transfer that proton. So as indicated here, this is the proton affinity of H2 and many other small diatomic molecules or atoms, and you see it has a low proton affinity compared to nearly everything else, important in particular CO. All right, so almost any molecule fundamentally that's observed in space in principle can be protonated. All right, so this is a nice example I like to show, and it's only fitting that Paula is here because this is in fact taken from a figure in her paper. This shows the astronomical spectrum of protonated N2. This is a really neat tracer because you can't observe N2 directly in these molecular clouds. It doesn't have a dipole moment. But you can infer its abundance by its protonated derivative. And this is actually one of the best spectra, if not the best spectrum ever measured for this line, and it's from space, right? So it has this very distinctive pattern here. I won't go into, other than to say that you have two nitrogen atoms, and they have a quadrupole and a very high spectral resolution. You can actually observe, observe that hyperfine structure. The outer nitrogen has a large quadrupole coupling constant. That's why you get this wider space triplet. The inner nitrogen has a small quadrupole coupling constant, and that's why these two lines have a smaller splitting. Another advantage of this is that you can infer the fractional ionization by this method. And in fact, people are using these, for example, to understand the kinematic motion in star formation by understanding how the relative velocity of this molecule and others change in the star formation process. All right, this is another neat example that I wanted to show. This is argonium, or argon H+, which was discovered fairly recently. And this actually came about during the Herschel Space Observatory when it was in flight, when it was launched. Radio astronomers very quickly found this incredibly strong absorption feature at 617 gigahertz. And they couldn't figure out what it was due to. They actually had considered argon H+ as a possible carrier, but because it's isovalent to HCl, but the laboratory frequencies of what they had measured versus what they had observed astronomically didn't agree. And what's amazing, this is the line shape. And the reason you get this very complicated line shape is because they're looking towards the galactic center. So we're over here, and you're looking all through these molecular clouds in the Milky Way to the galactic center. And this is indicative of the fact that the molecule, at the time unknown, is actually present at every single molecular cloud between us and the galactic center. What radio astronomers astronomers eventually realized is that it was, in fact, argon H+. And the mistake, if you will, that was made was they were assuming, or had perhaps forgotten, that terrestrially, nearly all the argon terrestrially comes from the decay of potassium. So the abundances of argon 36, 38, and 40 are shown here. Nearly everything on Earth is from argon 40. But in space, it's mostly argon 36. So as a result, once you make that correction for the isotopic shift, everything agrees. And what's neat about this, again, is because it has a very simple chemistry and a very simple destruction pathway. It now has been shown to be a very good tracer for very diffuse atomic gas and a very good probe for the cosmic ray ionization. So it's a very useful tracer in those areas. So we've done a lot of work on molecular cations, and I wanted to show this example. This is isocyanic acid, its isomers, and its ions. So isomers is a concept that we take for granted in chemistry, but in fact, this is isocyanic acid and its derivatives were really the driving force behind that discovery in the mid and early 1800s, when Liebig and coworkers realized that two substances could have different physical properties, but have the same elemental composition. All right, so this is isocyanic acid. We now know there are 4 stable rearrangements of that, 4 atoms. There are, of course, the 4 basic biogenic elements. And 3 of the 4 have been found in space, the lowest 3. The 4th one has not yet been found. All right. So there are questions about, in fact, how are these different isomeric forms formed in sources. We were also interested because of this question of isomerization. If you protonate or deprotonate, you, in fact, potentially can interconvert these isomers. So as shown here. So if you deprotonate isocyanic acid, you can form this OCN minus negative ion, which is thought to be actually the carrier in ice features. I was at a conference once and someone was talking about OCN minus, and it took me like 10 minutes to realize OCN minus was NCO minus. It depends on your convention there. But anyhow, or you can protonate and you can form a common one. So if you have a subsequent reaction with electrons, you can then interconvert this form to this form, or vice versa. So we did a lot of spectroscopy on the singlet isomers. We also were able to detect several protonated derivatives of HNCO, and that's what's shown here. So this is, again, this wider splitting is this quadrupole splitting from the nitrogen. We have a double peak line shape, which is instrumental, which is not of no concern here, but the rest frequency is the average of these two. And again, we can then, on the basis of these very precise laboratory frequencies, we then can step up and measure things much higher in frequency, the point of which is we want to provide accurate rest frequencies over the entire range of interest to radio astronomers. And in fact, that was found in this protonated form at the nitrogen was found in space by Herschel Gupta, who is here in the audience and now at NSF, which is a very nice piece of work. We've talked about a little bit, or it's been alluded to, about carbon chains. So again, this is a spectrum now at a slightly different frequency at this TMC1 survey. And it's complete, and again, it's about a 1 gigahertz wide window here. And it's completely dominated by these unusual cyanopolyine chains. And they're so abundant, we can see they're carbon-13 species as well. So you see off the scale here is HC5N, HC7N, HC3N is really way off the scale up here somewhere. And we see it's carbon-13 of even HC7N. So what's telling us is the chemistry which is driving this is very fast, and probably the importance of these barrierless reactions with radicals. And in fact, you can even see HC9N. I want to point out this is actually the motivation for Harry Kroto when he went to Rice University and discovered C60. He believed that long-chain polyions were the carrier of the diffuse interstellar bands. And he went there, and he didn't discover the carriers of diffuse interstellar bands, but he discovered C60, which I would argue is one of the most important impetus for not modern-day material science. All right. So I was disappointed. I went, I'm dating myself, but I went to the library at Harvard Chemistry many years ago, and because I wanted to look at this paper. It's a 2-page paper in Nature, and it was an older version, so they bind them up, and they were bound, and I got to the right volume, and I turned it outside, and I was amazed because there was a part of the Nature paper which was torn and tattered and everything. I'm like, this has got to be C60. I open it up, it's not C60 at all. It's the genetic sequence of the fruit fly. And I flip over to the C60, which somewhat worn, but not nearly as much. So anyhow. And so in the laboratory, we've then gone much farther beyond HC9N. Right? We've been able in the laboratory to detect chains as long as HC17N. All right? This is a spectrum, again, with this double peak line shape. It doesn't show here, but there are energy levels that are here. This is 217 AMU. That's twice the molecular weight of glycine. It's got a rotational constant of 50 megahertz. So every 100 megahertz, there's a line. All right? And these things are so well behaved, we believe, that we can predict with some accuracy, some confidence, still longer ones in the laboratory. All right? So this is useful in that, again, radio astronomers don't have to guess at what a line might be due to. They know the laboratory rest frequencies in space. All right? So what's remarkable, of course, is that people were able soon afterwards to produce C60 in bulk quantity and find things like graphene. And ultimately now, radio astronomers have been able to detect evidence for C60 and C70 in space, in this case based on its infrared spectra, right? And those are shown by Cami and coworkers. In black is the astronomical spectra, and red and blue are C60 and C70 respectively. So in fact, we have a highly ordered system that's just not this C60 and 70 found in space. As to exactly how they're formed, I couldn't tell you, but nevertheless, very compelling evidence for their existence. And perhaps equally or more importantly is, again, this aforementioned discovery of C60 plus in the diffuse gas, right? So this is one now, in black is the laboratory spectrum, in red are the center frequency for 2 diffuse bands. There are many, many diffuse bands. These are not the strongest ones. But nevertheless, this is very compelling evidence for the existence of C60 plus in the diffuse gas. And that suggests perhaps that there other carbon-type molecules may be the carriers of these stronger features. All right, so very quickly then, negative ions. This gets back to this idea of nature being much more creative than we are sometimes. So no negative ions were found in space since the advent of molecular astrophysics, about a 40-year stretch of time. And so at some point, I think the absence of evidence becomes evidence for absence, right? And so people had looked for small negative ions in space based on infrared spectroscopy, which was adequate, and they couldn't find them. The argument was by analogy to cations, HCO plus being one of the first cations found in space. So the idea is that we'll start with small negative ions, and we'll build up, because small ones must be more abundant than large ones. It's a totally incorrect argument, ultimately, right? Because the idea was there were a series of unidentified features that people thought might be C6H minus, but that would be larger than at the time, all of the cations that are known in space. So why would the first negative ion be larger than all of the cations? That wouldn't seem to have made sense. And finally is this theme, again, We don't know how they're made, but we know how they're destroyed. Everything that's a negative ion is weakly bound, and all you have to do is expose it to starlight, it'll fall apart. Okay, all those arguments are incorrect, because the key is for a negative ion, when you attach an electron to a molecule, you need enough degrees of freedom to cool it down, right? And so you can't have a small molecule. It's not very efficient at doing that. So that's why large molecules, in fact, have been found initially. So this is, in fact, again, the laboratory spectrum and the astronomical, they agree exactly to within a channel width in TMC1, which is about 2 kilohertz in this source. All right, so we have existence for this long chain negative ion in TMC1 and in other sources as well. So very quickly after that work, a number of negative molecular ions were found in the laboratory and then found in space. We know, and some of them now are very abundant. So C8H minus is roughly a third of all the molecules in the source IRC plus Sim216 are negatively charged of C8H. C6H minus itself has been found in about a dozen sources. We think for the longer ones, they're probably made by radiative attachment. For the shorter ones, it's hard to rationalize how that process could be very efficient. So instead, it's probably reactions of nonpolar negative ions, carbon chain ions with atoms. All right. A lot of metal-bearing molecules have been found. I think actually a lot more metal-bearing molecules will be found in the future, again with ALMA because of its high resolution, high angular resolution, and looking at evolved carbon stars, which are producing, in fact, many metals. So this is just one example of the first magnesium molecule found in space, magnesium NC. It was surprising because people thought magnesium plus was unreactive, chemically inert, but in fact, evidence was found for it. It was found in this outer shell of IRC, which is an evolved carbon star. And as indicated here, the central star is right here, the outer shell is here. So again, surprising, people thought a metal-bearing molecule will be found close to the central star. In fact, it's found farther out, very similar in distribution to C4H radical. And again, that's based on very precise laboratory data. So I think the last example I'm going to show you is something which we're pretty excited about, and that is evidence now for a polar aromatic molecule. All right, in this case, benzonitrile. So one of the really surprising areas is we see this unusual exotic chemistry, these highly unsaturated carbon chains, protonated and negative charge molecules. But people have looked for what I would say, or what my chemist friends would say, real organic molecules, right? Benzene rings. And those previously have been unsuccessful, right? They've looked for pyropyridine, various things. We know they're actually the building blocks of chemistry. I looked, in fact, at ChemAbstract Service. There's 135 million molecules in ChemAbstract Service. 80% of them are composed of one 5 or 6 membered ring, right? So when you talk to organic chemists, that's their idea of chemistry, right? Is aromatic molecules, big things. So these are, in fact, 9 panels of 12 that we have in which we found this source, found this molecule benzonitrile in TMC1. In black is the laboratory spectrum, the astronomical spectrum of different quality. In red is the prediction based on laboratory frequencies. All right. So if we found 12 lines to date, if I blow that up for you, again, it's such a sharp, cold source, we can actually see this nitrogen hyperfine structure. So again, in blue here is the observation, in red is the simulation, and we're again resolving features in space which are, 3 parts per million in terms of fractional accuracy, and that exactly agrees with what we have. The reason this is significant is, I think, twofold. Number one is, well, threefold potentially. One is it actually tells us for the first time we do have these aromatic molecules, which have long been predicted in the radio band but not seen. It tells us at some level this aromatic chemistry really is active, occurs at some level at, again, a source which is incredibly cold and incredibly low density, right? So this chemistry is occurring under, again, what would appear to be very inhospitable conditions to form rings. So it occurs at the earliest stages of star formation. And it's also significant because it's well known that the rate-limiting step in pH formation is the formation of the first aromatic ring. So once you form the first aromatic ring, usually benzene or phenyl radical, the difficulty of forming much larger organic systems, rings, is much easier. So on the basis of this, there are lots of possibilities of types of things that we're now looking for with the astronomical survey that is ongoing in TMC1. And we'll have to see how that all pans out. But it's, we think, a very exciting development. All right, so I will finish by emphasizing a few points. As I hope I've shown you, interstellar chemistry is really a rich and diverse broth of familiar and exotic molecules, things that the laboratory chemist or even laboratory physicist is familiar with, like water and ammonia and methane, but a large number of these exotic molecules. And again, they have very useful, very useful probes in astronomical sources. And there's no doubt, again, there's no reason to think the field has matured, that there are many more molecules likely to be found. And we need certainly very powerful facilities to make that happen, and ALMA will make that happen. I hope what I've convinced you is that their existence in space, the reason we can be so confident some bizarre molecule exists many, many light years away is because we have precise laboratory measurements which we can exactly compare, exactly agree. And we can do so with considerable confidence. And finally, again, this cautionary note, I would just say, based on my experience, and I've been guilty of this, is never underestimate nature's ability to synthesize complex molecules under conditions which you would think nothing would happen. And I think for that reason, I think there's good prospects that there are exciting and perhaps unexpected discoveries in store in the field as we move forward. So I will then just thank, there are a number of people who we've had the opportunity to work with and collaborate. It's been really a very fruitful interaction. A few of them are shown here. I'm not sure what they're doing, but nevertheless, and we have a number of collaborators and coworkers. Calvin actually is a postdoc in the group. He's here, and people like Herschel Gupta who continue to work with. So I will end, and thank you very much for your attention.
Hi, Mary Kershaw of ACS. How well understood are the mechanisms of formation of these exotic species?
That's a good question. I think it depends a little bit on the species, but I mean, I think for the small molecules, I think we have in most cases, a pretty good understanding in a general sense, the reaction mechanism. For larger molecules, I think it's much more qualitative. In that sense. And one of the things that's happening is with detection, for example, of isotopic species, you can look, for example, at carbon-13 substitution at these various molecules, right? And that allows you to test the formation pathway. So one of the oddities in many cases is the isotopic ratios are not constant along, even in simple molecules. So that we can then use to infer things like did the carbon atoms come from the same species, or were they come from two different species? So I think there's generally a qualitative understanding, with the exceptions of things like C60, perhaps, but I mean, but only a more quantitative for the smaller members.
Franz Geiger from Northwestern University. Thank you for a really fabulous talk. How do you accelerate the rate of discovery when I'm looking at 4 molecules a year to identify, right? I'd like to see this go up to 4 million a year. I mean, it's got to be out there, right? How many different ones are there? It's got to be billions. So what's needed to speed it up?
Am I allowed to say money? I have several thoughts. Well, I mean, there's no doubt that money is a factor. I actually think one of the big things we need is a collaborative effort. That in the U.S. in particular, there is kind of the one PI mentality in things like chemistry. Astronomy, it's a little different because of the nature of the facilities. But I think really having a collaborative arrangement is really the key, because we rely on other people. Radio astronomers rely on us. And so actually to have a tightly focused organization, where I think it would, I don't know if we'll get up to 4 billion, but we'll get, I think that's the key to move things along more quickly. I mean, really to connect the radio astronomy, to connect the laboratory, to connect the calculations.
Well, let's thank the speaker.